Okay, folks, let's start talking about section 13.1 in the book, Iterated Integrals. The first thing I'm going to introduce would be something called partial integration. Okay, this is very similar to the idea behind partial differentiation. Let's go ahead and take a look at this. I'm going to do a simple example for you first. Let's do this, maybe example 1. Okay, I'm going to write here the integral from 0 to 1 x squared y dx. Okay, now you guys remember the idea behind partial differentiation is if you had what? Two independent variables, you hold the what? If you're differentiating with respect to x, you hold y as constant, or vice versa, right? Now, in this integral, I'm only integrating with respect to x, so what I'm going to do is act like y is a constant here. Now, you guys notice from the actual form of the integrand, I could actually take the y out as a constant outside the integral, but I don't think I'm going to do that. I'm going to simply do the following. I'm going to go, well, if y is acting like a constant and I'm integrating with respect to x, I can use the fundamental theorem to go ahead and write my integrand this way, or my answer this way. And now, people, I was integrating with respect to x, so that means the limits of integration were in terms of x. In other words, x is going from 0 to 1 here. Okay, now let's evaluate that. So I'm going 1/3 1 cubed y minus 1/3 0 cubed y. And you guys can see a quick evaluation there in your heads. That's actually 1/3 y. Notice my answer was actually what? It was a function of y. Okay, for my answer. Okay. You don't literally have to write that there, but there it is. Okay? All right? So that's the idea behind partial integration here. Now, let's go ahead and do another example here of something where we're talking about iterated integrals. Okay? Let's just do an example of an iterated integral. Okay, you can read about this in the book also. Iterated integral. Okay. Here, I'm going to do the following. I'm going to integrate from 1 to 3, and then from 0 to 1. Or is that really what I'm going to do? We'll see. Okay, dx, dy. Okay, here. Now let's take a look at this. This is actually what we would call a double integral here, but we're going to compute it as an iterated integral, and I'll explain here. Now, something should look familiar to you here. Let's go ahead and take a look here. I'm going to use my little pen here. You guys notice here, I'm going to put parentheses right here on this guy like that. Do you guys notice that that's actually what? The integral just above in example 1. It's exactly the same thing. Okay, now, so what I'm going to do here is actually take that result and substitute in there what? The 1/3 of y, and then we'll get our answer that way. Okay? All right, so take a second here and let's do that. Well, let's take these off here. Okay, let's do this calculation. So, this was actually what? 1/3 y. So we're integrating 1/3 y dy. Well, that's easy. We can use what? The power rule on that. And we get what? 1/6 y squared going from what? Y equals 1 to y equals 3. Okay, later on after we get used to these, I'm not going to be going y equals all the time. But for now, we'll go ahead and do that. So I've got 1/6 y is 3, so that's 1/6 3 squared minus 1/6 times 1 squared. A quick mental calculation, that's what? Really 9 minus 1, which is 8/6, which is 4/3 for our final answer. Okay, that's an example of an iterated integral where we did what? We first integrated with respect to x, and then we integrated with respect to y. Our answer was what? Our answer is a number. Yes, it is a number. All right, let's do another example here in just a second here. There's one comment maybe you want to make when we get up here. Okay, let's come back up here for a second. All right. When I was integrating this with respect to x here, notice that I completely avoided using any sort of what? Leftover constant or anything like that. We all remember from the fundamental theorem of calculus here that what? I would have what? For an antiderivative, I would have a constant left over, and then what? It would just drop out of the calculation when I took the difference. Okay? Actually, let's go ahead and take a look at this and think about it this way. Wouldn't I have the following? Couldn't you argue? When I integrate from 0 to 1, x squared y dx, and remember, I'm acting like what? Y is a constant. Okay? We got this easily. This was 1/3 x cubed y. Now I'm going to include plus c, but really, you guys think about what I'm doing here. I'm taking an antiderivative here with respect to x. So actually, any function of y could be added on there. So that what? The derivative with respect to x is what? X squared y. Everybody see that? Okay? So that's actually a function of y. I'm using it for c. And then when I go from 0 to 1, I would get what? The same result I had before, because what? The c of y is unaffected by the fact that I'm going from what? X equals 0 to x equals 1. So I still get the c of y, even though that's a function. It ends up being dropped out when I take my difference, right? So I get the same answer I got before, 1/3 y for my answer. Okay? Alrighty? Now, in our previous calculation here on this, we would have had what here? We would have had the c on the end of this, and then the c would have dropped out. That's Calc 1. You guys will see what happens there. Okay? Now, here's something else I want to do here. Just maybe sort of do this in the opposite order. Let's suppose that I do that same example, well, in essence, the same example, and I do it backwards. Let's go ahead and do this. Okay? I'm going to go the integral from 0 to 1, integral from 1 to 3, x squared y. So I have the same integrand, okay? But here, in my previous example, y was going from 1 to 3. So I'm going to integrate with respect to y first, and then I'm going to integrate with respect to x, and then we're going to compare our answers, okay? Does everybody see, once again, that I'm going to have what? I have an inner integral here. This is an iterated integral. Okay, I need to compute this first. Okay, what's inside those red bars there? I need to compute this. What is this going to end up being? This is going to end up being some function of x, right? People would say that x or y has been integrated out. Okay, some people would use that terminology. Y has been integrated out. Let's go ahead and see that, though. Let's actually work this. Okay, so I'm going to do that inner integral first. I'm going to integrate from what? 1 to 3, x squared y dy. Okay, nice easy one. Let's see. Let's go ahead and integrate here. I would have what? 1/2 x squared y squared. Okay. You can ignore the fact that there would end up being what? A constant function of x that would drop out here because what? y is the only thing changing here. It's going from 1 to 3, like that. So let's actually do this calculation. What do we get here? We would get what? 3 squared is 9. It looks like we have what? 9 halves x squared. Y is 1. It looks like we have 1/2 x squared. So that ends up being what? 8 over 2, so that looks like 4x squared. So we're right here. That inner integral indeed ended up being what? A function of x. Now, to finish the problem out here, what we want to do, maybe I should do something like this. Go ahead and give that a name, I. Now I can make a statement here like this. I is the integral from 0 to 1 of what? 4x squared dx. Again, just using the power rule, 4/3 x cubed. X is going from 0 to 1. Okay, you guys can eyeball that in. You guys see that's 4/3. Wait a minute, that's exactly the same answer we had in the previous problem. Okay, so you guys see here, it didn't matter the order in which I actually ended up integrating in this particular problem. Okay, I wonder if that holds in general. Huh? All right, we'll see some more in just a little bit.